Good evening, sir or madam. This is Muhammad Khalil, who belongs to second year ECE department of ISL Engineering College. Here is my presentation about operational amplifier working as a ischemic trigger. Ischemic trigger. Comparator circuit with positive feedback are called as ischemic trigger, or we can say that whenever we provide positive feedback, it becomes ischemic trigger. It has two stable states of output voltage, that is positive saturated voltage and negative saturated voltage. Because of these two states, it is called as bistable circuits. In these circuits, the sine wave is converted into square wave, so it is also called as square wave generator. The very important phenomena occurs in the ischemic trigger circuit is that it is called is that the hysteresis. Here is the definition of ischemic trigger circuit. The output voltage changes its states whenever input voltage exceeds certain voltage level. So the input voltage can be exceed certain voltage level in positive direction as well as in negative direction. So for the positive direction, we have the upper threshold VUT, and if the input voltage exceeds in the negative direction, then we have lower threshold VLT. Next is the types of ischemic trigger. There are two types of ischemic trigger. One is inverting ischemic trigger and second one is non-inverting ischemic trigger. In this video, I am going to talk about the inverting ischemic trigger circuit. As the name suggested, ischemic trigger circuit, the input voltage or output signal is applied at the inverting terminal of the operational amplifier, and through resistance R2 is provided the positive feedback, and R2 is connected with non-inverting terminal of the operational amplifier to provide the positive feedback. Here Vf is the feedback voltage and it comes across the resistance R1. Vd is the input differential voltage and Vd equals to Vf minus Vin from the circuit. Now in the inverting operational amplifier, when it is in open loop configuration, we know that output voltage is equal to negative voltage of open loop gaining to input loop Vin. But in the inverting ischemic trigger, output voltage is equal to open loop AOL into Vf minus Vin, because Vd in circuit diagram is Vf minus Vin. So output voltage is equal to AOL into Vd. In this equation, we can conclude that output voltage depends on Vd. If Vd is positive, then output voltage is also positive. And if Vd is negative, then output voltage is also negative. Now this equation can also be written as Vout equals to AOL into minus Vin plus Vf. This shows the effects of positive feedback. So due to positive feedback, the input voltage is increases. Now the voltage across R1 is feedback voltage Vf. Feedback voltage depends on value and polarity of output voltage V0. If we want to find out the voltage Vf, we have to apply the voltage divider rule, that is Vf equals to Vout into R1 divided by R1 plus R2. In this ischemic trigger circuit, the output voltage changes its states only when input voltage exceeds some threshold level or some voltage level. So the input voltage can be exceed in positive direction or in negative direction also. If input voltage exceeding in positive direction, then the voltage level will be upper threshold voltage VUT, and if the input voltage is exceeding in the negative direction, then the voltage level will be lower threshold voltage VLT. So first I am talking about upper threshold voltage VUT. It is the value of input voltage that forces the output voltage to make the transition from positive saturation to negative saturation. When output voltage is going to positive saturation, that is positive Vsat, then the feedback voltage Vf will become VUT. Vf equals to upper threshold voltage VUT. If we put the value of Vf here, then we get VUT equals to positive Vsat into R1 divided by R1 plus R2. Since output voltage equals to positive saturation, so from this equation we can say that VUT is a positive value. Next is lower threshold voltage VLT. Lower threshold voltage is a value of Vin that forces the output voltage to make the transition from negative voltage saturation to positive voltage saturation. So if Vout equals to voltage saturation, then Vf will be equal to lower threshold voltage VLT. Now if we put the value of Vf here, so we get VLT equals to Vout into R1 by R1 plus R2. Since Vout is equal to minus V saturation, VLT will be equal to minus V saturation into R1 by R1 plus R2. So here from this equation we can say that VLT is a negative value. Now next is working of schemic trigger. Let us assume initially output voltage is at positive V saturation value. So in this condition Vf equals to VUT and VUT equals to positive Vsat into R1 by R1 plus R2, and this R1 by R1 plus R2 is a feedback factor of beta. So we can write VUT equals to plus beta into V saturation. As soon as Vin exits VUT and VUT is at non-inverting terminal of the operational amplifier, since Vf equals to VUT and Vin is greater than VUT and Vf is become negative. Since it is negative, the output voltage is also negative and output voltage equals to minus V saturation level. Now output voltage is minus V saturation and Vf becomes VLT. So VLT equals to minus V saturation into R1 by R1 plus R2, and this R1 by R1 plus R2 is beta. So VLT equals to minus beta into V saturation. Now as long as Vin is greater than VLT and VLT is at the non-inverting operation amplifier, and VT again become negative, and because VT is negative, so output voltage is also negative and output voltage remain as minus V saturation. Now output voltage is minus V saturation and again Vf becomes VLT. As soon as Vin becomes smaller than VLT, now VLT is greater than Vin and VLT is at non-inverting terminal operational amplifier. So VD becomes positive. Since VD is positive, output voltage is also positive and output voltage goes to positive V saturation level. Now Vf becomes VUT. So this process continues like this. By applying this condition, we can draw the waveforms for the inverting schemic trigger. So one condition is applied in the schemic trigger circuit is that whenever the input voltage is increasing, then the reference voltage is upper threshold voltage VUT, and whenever the input signal is decreasing, then the reference voltage is lower threshold voltage, that is VLT. So here this is the signal voltage sine wave, that is input signal, the upper voltage VUT which is in positive direction and VLT which is lower threshold voltage is in negative direction. So we see the intersection points on the signal in VUT and VLT, and we project these lines on the output voltages x-axis. So we draw the waveforms. So applying these conditions, we draw the waveforms from point 0 to point 1. We can say that Vin is smaller than VUT, and after that Vin is greater than VUT. So for Vin is greater than VUT, output voltage is Vout equals to minus V saturation. So we are drawing minus V saturation. But here we are seeing that after this peak point, Vin is decreasing. So our reference voltage will be VLT. So here we can see that from peak point 1 to point 2, Vin is greater than VUT. So for Vin is greater than VUT, the output voltage is minus V saturation. So our output is remain as minus V saturation. But after point 2, V in is smaller than VLT. So here the output voltage will be at positive V saturation. So we have positive saturation here. But after this peak point, V in is increasing, input voltage is also increasing. So our reference voltage will be VUT. So from this peak point to point 3, V in is smaller than VUT. So for V in is smaller than VUT, our output voltage will be at positive V saturation. So V drawn positive V saturation. After this point, V in is greater than VUT. So our output voltage will go to the minus V saturation. So this is minus V saturation here. So we can draw these output waveforms by applying this condition. So here we can say that the sine wave is converting into the square wave. Therefore, this is square wave converter. Now we are talking about transfer characteristics of inverting schemic trigger circuit. So we apply the condition which we have already derived. So whenever V in is smaller than VLT, then output voltage is equal to positive saturation. V in is smaller than VUT, then output voltage is become for positive saturation. Similarly, V in is greater than VLT and V in is greater than VUT, then output voltage is negative saturation. And here we have lower threshold voltage and upper threshold voltage, and here we have a curl. With respect to lower threshold voltage, first we will see that V in is smaller than VLT, then output voltage will go to positive saturation voltage. As soon as V in is greater than VLT, then output voltage will go to negative saturation level. Similarly, when V in is greater than VUT, then the output will be at negative saturation level. As soon as the input will become smaller than VUT, then the voltage goes to positive saturation level. So in this, we can draw the curl. The region between VLT and VUT is the dead band, and it is a voltage that is called as hysteresis voltage. Hysteresis voltage equals to VUT minus VLT. If VUT and VLT values are put, then we get VHV equals to plus 2V plus 2V sat into R1 by R1 plus R2. So from this curl, we can say that between VLT and VUT, there is no change in output voltage with the changes in the input voltage. Therefore, it is called as dead band, dead zone, or hysteresis band. So from this diagram, we can see that the output takes two values, that is positive saturated voltage and negative saturated voltage. Now, hysteresis. Whenever positive feedback is applied to the comparator, then the hysteresis occurs in the circuit. Due to hysteresis, the comparator output makes transition at different points when comparator changes its states from low to high and high to low. Next is effect of hysteresis, in which first one is noise immunity is improved, response time reduces, and the next is because of the input voltage, the output voltage does not change in the dead zone and hysteresis range. With respect to peak voltage, sensitivity of the circuit reduces. The last one is false triggering due to noise is reduced. Now, the advantages of schemic trigger. Due to positive feedback, the speed of response is increased. Due to hysteresis, the problem of relay chattering is reduced as the schemic trigger does not change its output in hysteresis range. By adjusting the upper threshold and lower threshold voltages, the duty cycle of the square wave can be adjusted. The monolithic schemic triggers are uncompensated, therefore they have high speed of response. The last one is disadvantages of schemic trigger. Sensitivity of schemic trigger decreases with increase in hysteresis because the circuit does not respond in hysteresis range. To overcome this problem, we have two solutions. The first one is, if value of Vin increases, then VUT is reference voltage, that is the output will be not changed at VLT. If value of Vin decreases, then VLT is reference voltage, that is the output will not change at VUT. Thank you. Thank you so much.